Hey everybody, welcome to Houdini Hangout. It's Monday the 9th of January, and we're going to be talking about a little bit more Vex tonight. I think everything went pretty well with the first couple chapters of the Joy of Vex. Hey, hey Lucas, nice to have you with us tonight. Welcome, welcome. Um, Everything seemed to go pretty well with it. And yeah, so we're going to be doing days 3 through 5, and the plan is to just kind of keep. Hey, Matt, how you doing? Glad to have you along for the ride again. So we're just going to be, going through the next few days here in the list. Trying to do it maybe a little bit quicker than we did last time without going too fast. But I really appreciate everybody's, feedback and comments and things like that. It seemed like everybody was really appreciative of just getting this content out there finally, I guess. So that's cool. And glad to have everybody watching again tonight. And hopefully kind of as we go along through the series, you'll find things helpful, and it'll really help you grow in your programming skills and things like that. So if you guys are looking to get connected with the community here around the stream, there is a web link here. Hopefully that will pop up. No, it is not. That is great. Thanks, Stream Deck. Let me just type it in chat here. HoudiniHangout.com. There you go. So if you guys go there to HoudiniHangout.com, you can get the Discord link. You can find the schedule for the rest of the streams. And my plan is to do a couple nights each week. So Monday, Wednesday, and Saturday for each of these next 2 weeks. It's quite a bit more than I usually do, but just in order to get through kind of all the content, in a timely manner, I'm thinking that's going to be helpful. And Saturday, we're going to do it at 1 p.m. Eastern time, so that if you're in Europe and you're looking to watch and connect, you'll be able to a little bit easier from that time. I think that's about all of the kind of housekeeping type stuff that I have. But so today we're going to be talking about, obviously continuing on with the discussion of Vex and talking about some new functions, talking about, just different ways to kind of work with these geometries that we had in the scene previously, and be able to visualize some new things, like using ramps and using some different functions and things like that to be able to kind of push our skills along further. So let's jump in and get this going. So just like last time, I have the content here on the side of the screen, just so we can kind of follow along together, so that kind of what I'm oh, okay, there you go. Had to move to Twitch. Nice. Well, yeah, whatever works. It's kind of why I'm on both of them, I guess, right? Hopefully wasn't anything weird about the stream from my end on YouTube, but I'm on both Twitch and YouTube. Either way, if you're looking to the chat delay is too long. I see. Interesting. Yeah. I guess maybe that's just a issue with the YouTube setup. I'll have to maybe look into that. It's like 30 seconds on YouTube. All right, I will have to look into that. Maybe that's on my end. Maybe I need to change the delay a little bit. Maybe I think I can tweak that a little bit. So I'll have to look into that and see how that's set up. So anyways, yes, I know there is a setting in there for how much delay there is kind of inherently in the stream. So I'll take a look at that. All right. So kind of starting off here, we're going to talk about one of the exercises that we had from the end of day 2, which was to turn these to turn this radial kind of black and white color into waves, into displacement on this grid. So I'm just going to just kind of jump right into this here, and we'll set this up. So all right, so we're just going to do a day 3 here for it, and let's just kind of start running through this, and we can set this up pretty easily. I'll get rid of these top 2 here. It looks like that's where we will start off here. So so what we're going to do instead, so we're going to take the D, and instead of doing distance, the distance function on that, we're going to do just the regular length function, because we're just going to do it to the origin. So what we'll do is we'll just do length, and we'll do at P here. So we've got that. We've got, we'll change this instead of scale, we'll change it to V scale like this. I'm just going to delete all of the spare parameters here, and we'll be making some more channels and things like that, parameters. So we'll add those in as we go. So what we have right now is we have, we're multiplying. If you remember this, let me just make this a little bigger here. If you remember, this times equals is a way to say multiply this variable by this. Yeah, there's a delete spare parameters. There you go, my man. Yep. It gets rid of all of them, but then obviously if you press the little plus button up here, it'll bring them back in. So yeah, I just want to say, like, too, if anybody has any comments or anything like that on what's going on during the stream, happy to get them in chat. Another thing too is I just want to say that I am actually been learning a few little tidbits here and there that I didn't even really know just by going through this. So it's been helping me quite a bit as well, or to some extent. I'm familiar with Vex, but there's some things that you just maybe miss as you're going along, and delete spare parameters. Yeah, there you go. There's one. So anyways, even as I'm going through this, I'm learning some new stuff. So it's been really helpful for me as well. So anyways. So, okay, so we deleted the spare parameters. We're multiplying it here. You can see we've got D, which is a variable, because we're not using that with this at, kind of syntax and saying it's an attribute, but we're saying that it's just a variable here. So this is going to be data that only stays in this attribute wrangle, if you remember from the last time we were talking about this. So we've got the variable D, we're multiplying it by this channel, V scale. So I'm just going to hit the plus, and that'll make our V scale channel here. And then after that, we're going to add time onto D. So we'll take this same thing and we'll say D plus equals, and do at capital T time. And that is a built-in attribute that we can use within any wrangle. So, okay, so we've got that. The last thing we're going to do here is, instead of saying at CD, we're going to say at p.y, and we're going to set that equal to the sign of the variable D. And so we'll change that there. And as we adjust this, we should see the scale that we have of this, this length parameter here. We're multiplying that by the scale, and then once we feed that into the sine function, it's going to give us these waves. And then on top of that, we're adding the time into it. So I'm just going to hit this little guy down here. So we've got it, animating the way we kind of, within a reason, within the actual 24 frames a second, instead of just letting it go as fast as possible. We hit this little clock down here. Okay, great. So we can adjust the scale of this here. We can adjust it as, as big or small as we want. We can have a ton of ripples. We could have just a few ripples going through it. Obviously that's the beauty of having these channels and sliders and things like that. So just to kind of talk about what Matt was saying here, if we actually turn this to a smooth shaded, it's not going to look right. You're not going to see these the undulations of this grid. If we do smooth wire shaded, we'll see that, yep, there's what's happening with the grid. There's these undulations, the sine wave flowing through that grid. The reason for that is that this actually isn't updating our normals. So what we can do here is we can go onto the tab here, and we can say update normals if displaced. So now we're actually updating the normals. So if we smooth shade this, we'll actually see that as well. So this is kind of a nice little trick. If you are doing displacement, it's actually going to update those normals for you. And you don't have to, kind of tell it to change those normals for you explicitly. It's kind of just you're deforming it, so we're going to update the normals and calculate those. So anyways, but this trick that we're doing here where we're changing it based on p.y only works for a flat grid. If we change this over to one of these other geometries, it's going to have some really weird consequences, like what's happening here. Here we've got some just really funky stuff going on because it's calculating it based on the distance to the origin, and that's really not what we want it to do. Because what it's actually doing here is we're not respecting the normal direction, right? We're not actually respecting the direction of that surface normal pointing, and we want it to actually undulate across that surface instead of just kind of globally in world space. So I mean, this could maybe be what you want, but it's a pretty funky looking effect basically. So instead of that, let's go back to maybe we'll just use Tommy here, and I'll just go back to his kind of default position here, and instead of that, so what we're going to do here is we're going to add p to n. So let's do this. So instead of this, we're going to do oops. So we're going to do at p plus equals at n. And so now we've got him kind of bulging out here, right? And what we need to do from there is give it a scale, right? So let's get rid of this stuff up at the top here because this doesn't really matter here. So let's now give it a scale that we can push this in or out with, depending, and we'll multiply this times the normal. So what we'll do here is we'll just take the normal and multiply it by a channel, and we'll call this push. So here we're setting up just a float channel, and we'll add it in there, and now we've got push. We can just see here that this is going to push him out based on the normals. This is basically just like a peak stop, if you've ever used one of those before, and we'll just kind of get this inflating Tommy geometry, right? So now instead of that, let's just go, let's copy this here, because we are going to go back to this other here. And so now instead of doing it this way here, so we're just pushing it out, we're going to actually take this with our scale and time and everything like that, but then add in what we just did there. So let's do, we're going to take p, we're going to plus equal to n, and we'll multiply that by the sine of d. So what now we're doing is we're displacing it based on the normal direction and then multiplying this function sine of d into that so that we get a wave based on how we're calculating that variable d. So here we'll do this, and we can see that we should be able to control that here. So we've got our scale, and as we go here, we should see this kind of freaking out, going back and forth, and it'll kind of go in and out and do some pretty wonky stuff here. But we probably want to have another control there so that it doesn't just strictly, hey, Zach, how's it going? Welcome to the stream. Nice to have you with us. So this is just basically setting it up to control how big the wavelengths are going to be, right? So what we want to be able to do instead is set up how big the scale of that actual displacement is. So what we'll do here is we have the n of sine d, but what we're going to do is we're going to multiply in another channel called wave height. So let's just do this. We'll make it just maybe a little cleaner here. We'll do it like that, and then we're going to add in another channel here. So we'll say channel, and we'll do wave height like that. And if we add that in, now we should have a way to actually adjust just the multiplier on this kind of displacement. So the scale of this displacement here. So we just give it a little bit here and really up this maybe to something like, I don't know, something crazy. We can just get a little bit of displacement here and kind of get this, we've got just a little something going on here. We could give it maybe a little bit more and it'll be, more like that, right? So So what we're going to, so kind of you have to play around with these settings a little bit, right? So he's saying he used the transform stop to scale him up because unfortunately the default wave height is good for a grid, but not good for Tommy just based on his scale. So let's scale him up. We'll scale him up to 4 here in this case. And let's go back here and we can do something like that. So now we've got him kind of changing scale, and we can also change the V scale here so we get a real wavy kind of thing going on. And now we've got, you know, a higher wavelength, or a shorter wavelength, I should say, and we can change the wave height here with this slider. So we've got these 2 different sliders that we can kind of introduce into it here, and this will give us the varying amounts of how much he's going to deform here, right? So we can change the wavelength, and we can also change the wave height, right? So that's all kind of hopefully making sense. What we're doing here is we're using the distance from the origin and using that, and then doing the sign along that as well, and that's allowing us to be able to then change the wavelength of D and scale it, basically multiplying that D variable by this V scale, and then adding in the time so that as time goes by, we're kind of varying those values, and that's kind of progressing through this sine wave as it's evaluating where we are on that sine wave. So this is just kind of a little bit of taking something like 3D geometry and allowing you to be able to actually have it displace along the normal, basically using that sine and multiplying by that to change it to go along the actual surface, and then giving you the multiplier of wave height to be able to adjust how high, you know, that wave ends up being. So if we look at the other geometries, they should all do relatively the same thing. Like, for example, here's the pig. And that actually looks maybe even a little bit better overall, because there's not these like kind of fine details where we're just pushing it by the normals will kind of make this geometry intersect in and out. This is actually maybe even a little bit of a cleaner. So you see, as we go really far here, we're going to have this kind of intersecting geometry based on the normals. But if you just kind of give this a little something like this and just kind of change our wavelengths here, we can get different kind of ripples and things like that on it. So so just using two different channels, 2 different parameters like that to be able to adjust your scales of either the incoming attribute or value into that sine function, or changing the value after the sine function, gives you those 2 different controls, one of the like kind of the wavelength, the other of the actual wave height. So yeah, so that's kind of the first little step here in continuing along with this. But now let's talk about some other uses for length. And we're also going to talk about another function called clamp. So let me just scroll down here so I'm looking at the right section. Great. So what we're going to do is we're going to switch back to using the grid. So let's go back to the grid here. We have our nice big grid here. I'll just do flat wire shaded, and I am going to set these back to just kind of very default values here. Oop, not 10. We'll just do 1. Great. All right. And so what we're going to do here is we're going to map our D value to just p.y. So we can keep this D right here, and we're going to get rid of this stuff in the middle. All right. And we're going to change this end. We're just going to do p.y again, and we're going to say equals D. So now we're evaluating the distance, the length of p, which is basically the distance of the origin, storing that as the variable D, and then setting p.y equal to that. So now we've got this kind of inverted cone, right? And what we can do here is we can add, we can multiply, we can divide, and we can subtract, and allow that to kind of change the height and the placement of where this cone is going to be. So we have this example here where we're going to multiply it by 0.2. So let's first do that. So we'll do D times 0.2, And we'll see that this is going to flatten this cone out quite a bit, because now we're scaling that way down. We're reducing kind of the scale of this quite a bit. And then if we take something like, if we do something like subtract 10 from it, that's going to then change the entirety of where that grid is kind of living. This displaced grid is living. So just like we, so that's giving us that offset. So whenever you do something like that, like add or subtract, that's going to kind of offset what position it is. In this case, since we're adjusting p.y, it's adjusting kind of the height in the scene in relation to kind of this this ground kind of plane. So instead, if we did something like adding 10 to this, it's just going to push it up above the ground plane by 10. And then similarly, if we took something like -1 right here and changed it to that, so changed our scale to -1, that's going to change the shape of it and actually invert the shape, right? So anytime you're multiplying by -1, that's inverting your results, right? You're taking your results and inverting it. So things that were positive will become negative, and things that were negative will become positive. We can see that right here where it's now going above in certain places and below in others. And if I just take out this, so if I just change this back to 1, we'll see that this will just actually kind of flip up like that. And since we've changed it to +10, that raises it up 10 units, in this case 10 meters above the ground plane. But we could just take that out as well and see how this is actually going to work, where it's basically taking more or less setting it right at the origin. Now it's up a little bit because these points aren't exactly at 0, 0, 0, so they have a little bit of a distance, so they're evaluating a little above the grid. And then if we take it by -1, we'll see that this whole thing will flip down below the grid, just like that. So again, we can take these values and offset them by things like, if we add 5, it's going to shift the whole thing up 5. If we subtract 5, it's going to shift everything down 5. So we're getting kind of these this concept of being able to scale by multiplying or dividing, and shifting or offsetting by using positive or negative numbers to kind of shift our entire value range up and down by that much. So, okay, so we've got, so we're raising and lowering with offsets. And what we can do instead of doing multiplying by, -1, what we could do instead is just say -d, and then say, in this case, he had +10 in there. So we'll just do -d +10. That's the same as saying d times -1. It's kind of a shorthand for doing it. It's a little bit cleaner too, because you know that you're just getting the negative value of d. So you're inverting d. So that's kind of a shorthand way of saying d times -1. So it's a little bit cleaner, a little bit easier to read. So say we just wanted a part of this and we don't want this entire kind of range that's getting shown here where we've got this whole cone. Well, we can use this function called clamp. And what this is going to do is stop the values from going past certain ranges of values. So if you look here, we have our p.y and it's going down to -18. And if we scroll down here, we're going all the way up to 9. So it's 9 above and -18 below. So what we can do is we can use this clamp to kind of change those values a little bit. So instead now let's take this and we'll keep it with D, right? So we can set it maybe back to D just to remember what this looks like, right? And now let's put this clamp function in here. So we'll say clamp, and we're going to open the brackets here. And the first thing it's looking for is the value that we want to feed into it. So the value we want to clamp is D. So we're going to give that as the first argument to this function. Then the second argument is going to be what's kind of the low end of that value that we want to clamp it to. And then the third argument is going to be what's the high end that we want to clamp it to as well. So let's look at that and what that does. Okay, so we've got some clamping going on here, but it's not maybe doing all that much right now. But we can see that we're limiting these values, right? And if we look over here, we can see that anything that would have been up above 3 has now been just limited to 3. We get some values in between here, and then basically everything else doesn't go down below 0, so nothing needs to be limited there. But let's look at this version that's a little bit more useful. Let's invert that and see what it looks like. So we'll say -D instead is clamped to 0 and 3. And here I am missing something, I think. More usefully, clamp negative D, 0 to 3. That does not seem like a more useful version of it, unless, well, let's do this. Let's leave it like this, and what we can do is we can do D, and we'll add an offset to it. Let's do this, D plus equals, and we can do something like 10, and we can kind of, oops, I didn't put a semicolon there, sorry. So we can add in some offset here and see kind of where this is going to clamp. Let's see, maybe if I do it in the negatives, there we go. All right, so if I do -5, -7, okay. So what you can see here, now we're actually getting somewhere, is as we change these values here, this offset. So we're adding an offset into D. So we're subtracting it down to 10. So let's just take a look at what this looks like. I'm just going to comment this out real quick. And what we can do here is we can take the same thing, and what we'll do instead is just do negative D and semicolon at the end there. Okay, so this is what negative D is looking like, right? So we can do -10. Let's see, maybe, oops, -8. All right, so let's do -15. So now we've shifted this up a little bit, and we're going to clamp it. So this is what it looks like without it, without the clamp. And let's do this. We'll comment this out, bring this back, and we'll see that now we're clamping those values that are at the top and the bottom. So we flatten it out. We're basically slicing it off at the top and just flattening it, and flattening it at the bottom below those values. So now we're keeping everything between 0 and 3. We've got a whole bunch here. If we look, we've got a whole bunch of values that are at 3. We'll go down a little bit here. We'll see there's a bunch of 2s and 1s and things like that. And once we get down to 0, everything's just going to remain at 0, right? So we've got this clamp function that's happening here, but it's basically keeping all of our geometry. It's not cutting anything off. It's not like deleting anything, but it's making sure that those values don't go outside of that range. So you can kind of imagine there'd be a lot of places where you might want to use values like this when you're making functions. It's really helpful for, when you're fitting values and things like that, to be able to clamp them within certain ranges. But what we'll see next is that the fit actually has a little bit of that built into it, right? So we can actually use the fit function to kind of do some of these things as well. So the fit will kind of help keep some of our ranges and clamp those. And then we can use this as well to then clamp a little bit more if we need to, around it. So we're going to kind of get into that next. So next, let's switch over to using this fit value, and it's going to take the value so they can only be between 1 and 2, right? So what we're going to do here is we're going to do p.y instead of clamp, and I'm going to get rid of this now. We don't need to see that because we kind of understand, I think, what's going on here. So let's take the fit, and we'll say D, which is our value again, this variable that we're using, and we'll go take the value of D and between 1 and 2. And we'll fit that to 1 and 2. So the incoming values we're going to take between 1 and 2 and fit those to 1 and 2. So let's do that as well. Again, semicolon. There we go. All right. So now we've got this value kind of clamped here between 2 and 1, right? And so it's just basically sitting right in those little that value range right there. So we have 2 at the high end, and it goes all the way down to 1 at the low end. So we're kind of using a little bit of a clamp in a way at the beginning there, because we're clamping the values to be just between 1 and 2, and then outputting them between 1 and 2. But now what we can do with it is we can actually take it and say, okay, instead, let's go 0 to 10 on the output, right? So what this is going to do is kind of make this really exaggerated step, right? So it's taking that and scaling it up so that it's stretched to sit between 0 and 10. So now if we look at the values, instead of them being between 1 and 2, on the low end they're at 0, and on the high end they're at 10, right? Just like we have set here, between 0 and 10. So that fit is doing something very similar, and it looks almost like what we were just doing with the clamp function. But then we can take something like this and kind of play around with using both of them in conjunction. So let's just kind of go back here a little bit. So we'll take float D and just set that equal to the length of the position, and then we'll take D and we can fit that. So we'll do fit D and say, and we'll take the incoming value between 1 and 3 and set that equal, or set that between 1 and 0. So we're basically taking that range and flipping it, right? So we're taking the values between 1 and 3, and instead of setting them between 1 and something, we're going to set them between 1 and 0. So we're going to be going down instead of up with that. So we're flipping and we're clamping there too. And then we can do another clamp here, just kind of like a sub clamp on this value, and say D equals, we're going to say clamp, and that is going to be, again, since we're still working with D, we'll set that to D and say 0.5 to 1. So we're clamping it again in between 0.5 and 1. So then we'll take we'll set the variable p.y equal to D. Great. And I said clammo instead of clamp. There you go. Some little bit of, you always have to kind of watch out for, little typos and things like that in Vex. Unfortunately, it isn't super, forgiving with those types of things. And you do have to watch out for that and make sure that you don't put typos in there or anything like that. So, it's always can be little things like that, but usually there's little highlights in there. You can see the red underline came in and I could see instantly, oh, yeah, I mistyped there. So, okay, so we've got this, flipped and clamped, and then we did a little sub clamp to it here as well. So what we're doing here is, if I say instead, let's clamp this to 1 and 0, this is what it looked like before that, right? So we just had it set between 0, sorry, I should set it this way, 0 and 1. I think that's correct. There we go. So we had the clamp set between 0 and 1. I shouldn't have flipped it that way. It was trying to do some stuff that didn't make sense. So this is basically showing that whole range, right? Because we have our value. We took the incoming value from our fit function between 1 and 3 that we were bringing in and setting that to 1 to 0, right? Or 0 to 1. And then here we're clamping it. So before we had it clamped to 0.5, and that's just going to shift the ground up a little bit, right, in this case. So this is where we're kind of taking a fit and a clamp and using them together to kind of, set up different ways to control your geometry as you're working with it. All right. So, but instead of doing it this way, instead of having all these things just set with hard-coded numbers, really the beauty, like we were talking about last time with Vex, is that we can set this up with channels, right? So we can actually set channels here that will do all of these things for us, right? So instead of this, let's get rid of our clamp. We're not going to use that for right now. We're just going to use the fit. And let's add some sliders, right? Some channels. So let's do a float, and we'll say in min, and we're going to set that equal to ch, and we'll call this fit underscore in underscore min. And then we'll just copy and paste these and just kind of make a whole bunch of them, right? So the first one's in min. The second one is going to be in max, and we'll call this fit in max, like that. And we can copy these, right? And we can say out min and out max. And here we'll say again out max. All right. So now we have these channels set up here, right? Let's delete the spare parameters because we don't need those anymore. Those are from some older stuff that we were doing. I'm going to get rid of this day 2 here as well. Okay. So now let's take these float variables that we set up with the channels, and let's set these end arguments in this function to those values so that we have control of where we're doing our in and outs, values from. So the first one is going to be in min, and then the second one's going to be in max, and then we'll say out min and out max, just like that. Great. So now we have a bunch of channels set up here, a bunch of parameters. Let's turn that on. Let's hit our little create spare parameters from our unset up channels basically. And so now we have all of these sliders here that allow us to control these. And so as we start playing around with these, we'll see that we can set our values to, different stuff and kind of play around with how this is going to work here. So you can see that as we set these different in and out values, that is going to kind of clamp where this incoming geometry is. Hey, how's it going, man? Glad to have you with us. So now we have a lot more control over what we're doing, right? We're not having to go in and retype these values all the time, and we can use our little ladder here to be able to adjust these values on the fly. In fact, I can just set these to 0 and maybe round these around 13 and 6 just to kind of give it a little bit more. So we can use this in the out functions to scale it, right? So we can use the out values to kind of stretch where these these values are going once they kind of get clamped on the incoming data. So we're taking it, we're saying clamp it here at 0 and 13, right? So we can kind of play around with that. That'll change kind of the shape of what we're doing, right? If we flip these around, it's going to invert the shape. So we can kind of keep tweaking these around, play around with that. And then here we can adjust, where those values are being, kind of remapped to. So this is I think a really powerful way to kind of visualize how you can use Vex with the with a function here, just a fit function, and use that to reshape this data as it kind of flows through your Vex code, right? So in this case, we're just taking a variable D, we're using some channels to adjust the values, kind of on the fly, and then we're just putting that into p.y, updating our y position of our geometry with the value of D. So this is kind of, I think a pretty interesting first step in kind of understanding some of the way to use these channels and to use, like a user interface here to be able to start controlling what your functions are doing. You can see kind of the way that Matt was playing around with these values here in his little screenshot. Very similar. You can kind of just tweak these values to your heart's content, and using just a simple couple functions like length and fit, we're able to kind of play around with these different values and get some kind of clamped geometry going on here. So it's really fluid, and I think this is what makes Vex really interesting. So, okay, that's day 5 right there. So that was a pretty short little lesson there. Hopefully you could follow along with that pretty well. And there's some exercises at the bottom here that I would, again, encourage you to go out and do as you're kind of watching along with this. Pause the video, sit down and say, okay, let's go through these exercises. Like, try to incorporate clamp in the above setup. See if you can make it do something interesting. Okay, so take clamp, put it into this setup here, see what you can do with it. So set P based on waves generated from the sine of D, but see what happens if you fit and clamp before sine, after sine, or both. So thinking about taking your sine waves and clamping those, I think hopefully you can start to maybe visualize what might happen there, right? We're almost kind of doing something similar to that, where you could maybe shape the way that your waves are looking, right? So another exercise, waves that start from 2 points and mix with each other, right? So maybe we'd be doing something with adding, multiplying versus equal, and how you can accumulate results over several lines. So he's basically saying, using adding values in to be able to make, multiple, using 2 points to basically have sine waves kind of mixing together with each other. So, and also try maybe and build some of these examples with VOPs and see how that feels versus doing it in Vex, and what feels like a faster result. So there you go. There is day 5 of the Joy of Vex. If you guys that are watching have any questions, you can always drop them in chat. Love to hear from you guys as you're watching and kind of going through this. If you're following along, awesome. If you're just kind of here to absorb the knowledge and maybe go back and tweak it later on, that's great as well. So so if you guys have any questions, I'd love to kind of answer them. But otherwise, if not, I think we'll just keep rolling along. Like I said, we're going to look to do about 3 days in each of these streams. I'm hoping that each of the days will kind of take maybe about 30 minutes, 40 minutes, 30, 40 minutes, something like that. So we'll be able to get through 3 in each of the next upcoming streams. And I think that kind of fits along pretty close with what Matt kind of had intended with the time that you'd kind of put into these individual, just lessons, basically these individual days of learning. So, all right, well, let's keep rolling along. And if you have any questions, I can always jump back and kind of talk about it a little bit. But we're going to go to the Joy of Vex 4. Good. Yeah. Hey, there you go. Even Matt is able to, to maybe take some things along with it. I might have misunderstood stuff too, but yeah, there's always room for improvement for everybody, right? So, yeah, good. I'm glad it's helpful for you too, Matt. Good. Yeah, hopefully I didn't totally miss something there, but I can always post a little addendum if we need to, if there's was an error or something like that. But anyways, so let's jump on to day 4. And in this, we're going to start talking about one of the things I think is really fun to work with, really in any CG program, any DCC, but it's working with ramps, right? With curves and ramps and things like that. And this is something that might be a little confusing maybe at first, just because of the way that you're kind of representing X and Y values with multiple, you're setting values based on X and Y, but hopefully we'll be able to explain it well and get you kind of comfortable and familiar with using ramps and how they work in the context of Vex code. So let's just make another node here. I'm going to clear this all out, and I am going to delete all our spare parameters here. All right, great. So we're back to just having a grid here. So basically what a ramp ends up being is a 0 to 1 XY graph, basically. As you can see here, there's a few different examples of what these ramps will look like. The default is a linear ramp that goes kind of up a hill like this, basically just a line straight up. And it's in its default state, basically what you're looking at is a ramp, or how it maps the values is basically 0 to 1 on both the X axis and on the Y axis, right? And so what happens is you tell it what variable you want to become the X axis, right? And what it does is it takes the value of that variable and looks up the position of it and sees what the Y value should be at that place on the X axis. So that's why you can take something like, say it was something like distance. And if the distance goes from 0 to 1, you could take that and map it to other values here. So maybe you'd want to do something like invert it. Well, you could just flip that slope to be going the other direction, and that will just invert your values, right? It'll take 0 and set it to 1, and take 1 and set it to 0. So that's one way that you could just initially tweak the values. You could also make a makeshift sine wave here and kind of just put some points in there and squish them around, or do something random, just kind of randomly make lines go up and down and all that kind of stuff. So there's a lot of different ways that you can take these values and kind of to tweak them and work with this just 0 to 1 range and get a whole bunch of interesting results out of it, right? So all right, so let's start actually putting some Vex down and start looking at how this works. So let's look at this distance example from the previous lesson. And I guess I should have just not deleted that one. So let me get rid of this. And we'll go back to this. And so what we're going to do is we're going to keep just float d is equal to length p. So we'll do that. I'll get rid of these guys here. And we're going to be doing, so we'll just do this for right now. We'll kind of fit the rest in here. So let's delete the spare parameters. So we have float d. So this variable is equal to the length of the vector p. And what we're going to do is we're going to multiply this by a scale. So we'll do d and do times equals, and we'll make channel, scale, just like that. Great. Then what we're going to do is we're going to take, we're going to set the p the y component of position here, so at p.y, and we're going to set that equal to chramp. Oops. And we're going to first, at first it's asking for the name of this channel, right? So we have to name it. So we're going to call it just something simple like my ramp, like that. And then it's asking what, what value is going to be evaluated. So we're going to evaluate D in this ramp. So there we go. We're setting the y component of P to this ramp. And so let's just add that in, and you'll see that this is going to make a new ramp right here. Make this just a little bit bigger so we can kind of see this. And so now we've got our ramp value here that's coming in, and I'll just make sure the flag is visible there. And so now we should have, oh, the other thing I didn't set was the scale. So we're just going to set the scale here, right? And so as we multiply the scale, that's going to change how, it's going to change how far basically we're looking. It's going to change the scale of this incoming D value to be able to say how far away basically are we going to be looking up into this ramp. So there we go. We've got the scale to kind of change the size of it. And then we have our ramp here that's going to adjust kind of the slope of it, right? So, okay, so we have that set up, but let's kind of start adding some other stuff here to make it a little bit more interesting, right? So sorry, I think something. My apologies. Seems like something is not working right here. No, okay. I think it is working properly. Okay, cool. So we're just adjusting the scale so we basically have it so that this is going to scale across, the entire grid. Okay, cool. All right, so we have scale. So let's add some time in here or subtract time from it. So we'll do D minus equals and then use that variable, that attribute of time that's built in. And then we will take, so we've got our p.y set to chramp. And here we can then, after the fact, after we add that ramp in, we're going to change something to change the actual height scale of it. So let's go in here and say at p.y, and here we can do times equals, right? So this will, times equals, and this will multiply it by whatever we put after it. So now we'll say ch, and we'll say add a channel in called height, and do it just like that. We'll add in that parameter as well. Now it has actually flattened it because height got set to 0. So as we scale this up, we can actually make this quite a bit higher like this, right? So we now have our height scale, and we have the scale kind of the incoming value from our length function. So here you can see how we're scaling this along the geometry, kind of allowing it to spread across the whole geometry, and how we're adjusting that then with the height at the end. So here we're taking this ramp and multiplying it by this height value here. So maybe we'll just set that to like something like 10, just to make it a nice round number. Cool. All right, great. So now let's kind of play around with this this ramp and just kind of see what's going to happen with it here. So now we just have one nice big ramp, and if we hit play here, we have some animation going here, and it just kind of flattens out the grid here, right? And so that's adding in time here, so we've got some animation to it. And so let's kind of tweak this a little bit, and let's first take a clip and let's split this grid so we can kind of look at it along its edge, right? So let's add in a clip. And what we're going to do is we're going to set this to clip along. We can actually do it this way. We'll just clip it right along this kind of this XY plane here. So now we can kind of see right across it like this. Right? Oops, sorry. There we go. So now we have this, and we can see that we can actually start to adjust this this ramp here, and it'll actually adjust the way that this is being handled basically in our okay. Used to implicitly modulo. Okay. So what Matt's mentioning here is that this is actually something that is a new feature, quote unquote, an update to how ramp works. And so what it used to do was it used to actually modulo the values, which meant it would kind of repeat the values over and over. And that makes okay. So that's why I'm like, okay, it said it's gonna. I'm reading through what that's doing here, and I had read this through yesterday, and I was kind of expecting it to do something different. So that explains why this is not doing what I was expecting it to. Okay, thank you, Matt, for clarifying that. So basically, what we're getting here is a different, it's not. It used to just repeat the values, and now it is clamping them by default, and that's why things are looking a little different here than I'm expecting them to, and how they look in this value. So hopefully this will help, and Matt says he's going to go through and update this so that we'll make sure that so you don't run into this issue as you're going through it. So yeah, so after D plus time, right. Okay, so we're going to say. So we'll say D is equal to mod. Yeah, okay. So this is going to modulo 1 right here. I see what he's writing. Yep. Percent equals. Right. Okay. I was like, is that right? Okay. There we go. So now that should do it. Yes. So unfortunately, sometimes things do get changed in the software. So let's see. Is that? Okay. There we go. So that is, I think, what we were looking for. So. And that's why this was not looking the way we were expecting it to earlier here as well. So now we're actually getting the attributes the way we would expect it to, where it's actually repeating and kind of going around. And this is what Matt has kind of, you'll see in the demo here as we go along. So now everything's back to normal. Thank you, Matt, for clarifying that with me. I did not know that changed either. So yes. Anyways, continuing on. So where were we here? Let's see. Add ramp, scale, ramp, change ramp shape. Great. Okay, so what we're going to do is we're going to, so we have the ramp. We can invert it so it starts high, ends low. So we can do, we can do like this. We can take this guy and put it up here. We can bring this down like that. All right, so now, bring it down like that. So now we've got it starting out high, ending low. And again, this is cut. So let me just go back to how this looks here so we can kind of see this a little bit better, maybe without it being clipped just at first. Cool. All right, great. So now let's just make a rough sine wave using the ramp, right? So what we can do here is we can take this and just kind of draw out a little sine wave here. So we're going to have it go up high and then maybe down low. Down low like this. Cool. So now we have like a little sine wave going on here, and we can, now as we change the scale, there we go. Now we're getting something that looks a little bit more recognizable here. So let's just change the height back a little bit here. Cool. So now we're getting some waves that we can actually control. We could maybe push this a little bit, you know, a little more this way, something like this. Cool. All right, so now we're getting something that looks a little bit more normal-ish. Great. So we've got now a little like kind of fake sine flow looking thing going on here that we can control the shape of it, right? And so let's, and this again here, he's saying kind of a misbehavior that ramp has an implicit modulo, but actually it has an implicit clamp now. So that's actually backwards now. So, but we can actually see how this will affect. And as we change the scale of this, now it has the kind of this modulo happening, which basically it repeats your value over and over as you go between 0 and 1. It kind of loops back around, and it just keeps the remainder basically past me weren't, yeah. So anyways, yes, he was saying that's a little warning from past me to present me, but so yeah, cool. So we've got time in there, we've got the ramp, we've got multiplying it by height. So everything is looking pretty good right there. So let's now add in this clip, and we can actually look at this maybe a little bit closer here. So now we can see these waves basically from what we had shaped here, more or less. So if we take something like this and we just make it into straight lines like this is going to turn it into almost more of like a triangle wave, right? So we can do something like that. We could push it more like this, and it's going to turn it into almost like more of like a sawtooth wave, right? We can shape these all sorts of different ways. So we can change it to be up just for a short little bit and then have a big flat section here. And we can change the scale by just adjusting this value here as well. So this is a way that you can actually come in here and shape these waves in all sorts of, different ways using this ramp, right? So you can make all types of different shapes just by changing how the profile of this ramp is pushing the Y value up and down as we look through that value that's getting passed to it by time. So, right. So that allows us to be able to kind of dial that shape in as we want to. And I like how Matt says this. Note that by easy, I mean easy until you start swearing at the ramp UI. So one thing that we should just note here is that this does stay within the 0 to 1 range. And what we mean by that is that on the low end here, we have 0 for the x-axis and 1 for the x-axis. And then at the very bottom down here, if we look this way, we're going 0 on the y-axis up to 1 on the y-axis. So that's something that definitely limits us there. And then if you change them to other types, they can get a little bit weird on us and stuff like that. So there's some things you have to like copy and pasting. Oh, you can? Oh, that's right. Can you? Oh, yeah. Pff. Look at that. Cool. Hey, I didn't even know that. Cool. So yeah, if you wanted to go above, so I guess maybe this chapter we might re-record possibly, but yeah. So what Matt just said there is actually now you can push it past these values. Now I don't think you can push it past. Oh, no problem, Matt. Hey, we're just working through it. We'll figure it out. Anyways, so yeah, so position is clamped, values aren't. There we go. Perfect. So the x-axis isn't clamped, or is clamped, but the position you can actually put, or the value you can actually push up and down. So we can push the value way up if we want to, or actually way down in the negatives. So that's kind of an interesting thing. That's you can't. I don't think you can just do that by grabbing these points originally. Exactly. Now we can really appreciate how it used to be versus how it is now. I say a lot of times people don't appreciate all the advancements that come in some of these things. Like, oh, I remember back in the day when you couldn't make it go past 0 and 1. Now we can enjoy that more, Matt. Because I didn't even know that was possible. So here we go. We're all learning, right? Okay, cool. So let's take this next example and kind of put this in here and start to play around with this a little bit. So we'll leave this modulo expression, or this modulo value in here, just so that it does actually repeat and doesn't just clamp it to the range. So let's just, there's actually some presets in here, so we can just say linear. So we're going to set it right back to where it was originally. And so, okay, so we've got our length function set to p, we've got scale. Let's instead now just add in time. It looks like we're just switching that around a little bit, so it'll add the time in. And then let's now set this to d, let me just think about this. We're going to probably want that before we do the modulo, I want to say. Let me think about that. Yeah, I think we're going to want to do the modulo after this. So let's just... Yes, because it's going to modulo before it goes into the ramp. So we're setting this back to the original value by adding this one line in here. So we're going to put the stuff in between. So we're going to put that in here. I think that's the correct call. So let's do this. D equals sine of D. D equals, and we're going to do, so first we're obviously taking all the stuff we did to D and running the function sine of D on it, right? So that's going to be the next step there. And then we'll fit that, right? So we're going to take a fit function here. And since we know that sine goes between -1 and 1, we'll start with those as the incoming values. So we'll do -1, comma 1, and then we'll go up. We're going to set that to 0 and 1, because that's kind of what that's what this is expecting coming in, right, into the ramp, right? We can't set it outside of that 0 and 1 in the x-axis, but we can, again, like we said, we can push it higher or lower if required. So now we're fitting it to that x-axis and in that 0 and 1 space. All right, so I think that should work like that. Nope, semicolon. There we go. All right, let's take a look at this. Okay, what are we getting there? We're getting a little weirdness. Is that something I'm doing? Might just be a little like floating. Okay, cool. So let's do this. I'm just going to pull this back up and take this clip out of here. All right, so here are our waves now that we've created with a sine function, right? And so now what we can do, we can take those sine waves and then clipping and shaping that result using our ramp. So, so here we go. Here's this. I'm just going to take that out just so it moves a little bit quicker. And now what we can do is we can actually shape these sine waves using our ramp, right? So say we want it to be sine waves, but instead of just regular sine waves, we want there to be maybe some extra little jagged elements in it, right? We can add, we're gonna be using our ramp to look up on that value and adjust the shape, right? So now we can do things like this. We could also just, I don't know, we can play around with this kind of to our heart's content and do all sorts of different stuff with these values here. So yeah, we can kind of play around with them like this. Could maybe do something like that where it'll come up and then sweep kind of down right at the end. All sorts of different options here that we can kind of play around with, in these values, right? So we could also do like Matt's showing here. We can take the end of the ramp and kind of pull it back. So let's do that. just to see what that's doing as well. So as we take this and bring it back, it's going to kind of make a little flat spot, right? Because that's going to be only, so when it gets to this part of the sine wave, it's going to remap that to only be up at 1, right? Instead of going back down or anything like that. So yeah, there we can see that kind of high spot, and we can pull this in and out, and that's going to reshape the way that the way that that wave is being evaluated in the functions. So the last note that is made here is that we're taking the value of sine, right, which is -1 to 1, and we're looking at that right here, right? And when we do that and take it from some UV Vex related stuff. Well, I'm not 100% sure how far into that we will get over the course of this series, but yeah, I'm just gonna right now. I'm just going through each and every day of this Vex, Joy of Vex series. I'm not sure exactly if and when we'll get into UV related stuff, but I have a feeling we're definitely going to get there at some point. So yeah, so I think as I kind of go through the different days, we'll definitely see when we get there. In fact, I can go back and take a look and see if there's a day that maybe mentions that. I'm not sure if it has a little description of each day, but yeah, we're kind of going through, I think there's 20 days total. So I have a feeling at some point in there, we'll be looking at some UV related stuff. But anyways, so with going from -1 to 1 and fitting that to the value of 0 to 1, that's actually called normalizing. So we're taking these values that are between -1 and 1 and bringing it now into this range of 0 and 1, and that's called normalized values. So this is important for vectors, especially if you're looking at things like normals and things like that. When you want to describe a direction versus something like speed, having normalized values is really important. And we'll get that, like Matt says here, we'll get to that in some later lessons. So, okay, there we go. That is basically the extent of day 4 of the Joy of Vex. And this might be something we have a little addendum if Matt ends up, if he changes some of those things that I think he's going to be doing. What's the use of normalizing, and what are some of the various methods of setting them up? Right. So, yeah, so this is normalizing values, right? Because we're looking at just a float, right? So in this case, we're taking our p.y values and normalizing them, right? We're also then multiplying them at the end here by height. But if we change this to 1, right, we can see that these values never go outside of that, 0 and 1 range. So it's going to go all the way down to 0 down here, and at its highest, it'll go up to 1, right? It's kind of like a fit 01. No, not quite, because a fit 01 is another function we'll get to eventually, I'm sure, but that's kind of the opposite, where you're taking something that is incoming at 0 and 1 and setting it to a wider range. And yeah, we'll get to that probably in a little bit. But so normalizing is going to make it so that when you have these values maybe that are all Right. Okay. You're 100% right. Makes sense. So it doesn't require that value there. Yes, because we're already okay. So what Matt's saying basically is that we didn't need the modulo there to make it look proper, because we're already fitting it between 0 and 1. So we don't need to be doing, doesn't need to have the modulo in there. But I'm going to just refresh this because Matt said that he's made some adjustments to this. So let's see here. Yeah, there we go. Which I'll explain in future lessons. There we go. All right, so we're all updated here on the wiki. So that'll be great. Hopefully that you'll be able to follow along a little bit closer than that. Your version of the document won't perfectly match mine. Oh well, if you're looking at some of those operations and things like that, we actually went over those in the last couple chapters. Basically, plus equals is just a way of saying add whatever value comes after that to the value before that, the variable before that. So in this case, we're talking about plus equals. We're just taking the variable d and adding time to it. This is just a shorthand way of saying, instead you could write it this way, right? Equals D plus time. So instead of saying D plus time, D equals D plus time, you can just say plus equals like that. So anytime you see something like that, plus equals, that is, minus equals, things like that. The two equals is something with logic that I'm sure we'll get into later, but, so that's one part of it there for sure. But as far as, sure. So as far as the normalizing thing goes, that's really important in vectors, things like normals, directions, things like that. You a lot of times want those to be normalized values. Those will come up a little bit later in these lessons. So yeah, there's some things that we want to AI chat. Well, I'm not really going to comment on that right now because I think there are certainly places where that could be helpful in the future. But even just seeing some examples within Houdini, I saw some of the developers posting the other day about things that just weren't right that they were saying about functions that don't exist and things like that. So I think it's a promising thing to be able to help you learn and maybe experiment with some things. But I think there's a couple things. People are always going to, for a long time, I think, I don't know how long, but people will be programming still. And so I think that'll be something that'll stick around for a little bit, but I'm not going to get too into that whole discussion right now. So it's an interesting thing. We'll see how it kind of develops over time, and we'll see how it goes. So anyways, so this page is now updated, so that's good. Thanks, Matt. And we'll follow along with some of those little issues that we ran into as we were going through our functions here. So great. That is day 4 of the Joy of Vex. Maybe we will be going back and revisiting this just because things kind of were a little bit confusing there. So hopefully, if you guys have any questions about how this particular section works or what we were doing here, I'd be happy to kind of, go back and address any of the things maybe that, got away from us. Hopefully it was understandable what we were saying about the modulo functions and what Matt mentioned. And if we need to, we can go out there. It's great to have Matt here. It's good to have someone to be able to make these corrections on the fly, I guess. Right. So I definitely was not expecting that, but very grateful for that. So, All right, cool. Well, let's just keep rolling along and see where we get here, because now we'll actually be talking about Modulo a little bit. So I'm just going to take a little break here for a second. If you guys have any questions, you can always drop them in the chat, and give me just one moment. All right. So this next section is going to mainly talk about Modulo, which is what we were using to kind of fix those inherent issues that were kind of popping up in that last chapter. So this is going to hopefully answer any of the anything that might have come up there that was issues. I'm just reading Crossfader's question here, which is just saying, are these functions constant in terms of their use in production? I'm not 100% sure what you're asking there. Now, I'll say this, if you're looking at in production uses of things, and I'm sure Matt could speak to this much better than I ever could because he's worked in big studios and things like that. But fit functions and all these different things are going to be things that are used in those scenarios as well. I mean, ramps and all different float channels and integer channels and all that kind of stuff. Those are all the building blocks of these of working in Vex. I mean, obviously you're going to get into more and more different advanced functions that you're going to use in those scenarios, but all of these things are things that'll pop up, I'm sure, time and time again in large, and in my case in any smaller production stuff that I've used for doing any Vex. So yeah, these are definitely things that are constant across the industry. I guess if you're asking, So, okay, I suppose the logic behind... Yep, exactly. So the logic behind what you learn, yeah, is first the core functions you'll be encountering. And like Matt said, yeah, he focused on a handful of, functions and things like that you're seeing all the time across production. So yeah, for sure. These are definitely really, really common things. They're stuff I use all the time, fits and length and adding in channels and ramps and all that kind of stuff. So yeah, super, super common in my workflow and in all the workflows that you're going to probably come across out in the industry. Cool. If you're looking to see other content and things like that, for right now, we're going to be doing a little series on Vex right now. So that's what we're going to be sticking to here. But I do have some stuff on my channel about KineFX. So if you look back, you'll see some KineFX related stuff. In fact, we had Michael Goldfirebaum as a guest, and he walked us through a whole bunch of KineFX, which was really awesome. So that is your place to go if you want to see any KineFX stuff. Great. So, all right. So this next section, we're going to kind of start off by understanding what, modulo is, right? And so, so when you do long division, right, what you have a lot of times are, yes, the page that I'm referring to, my bad. I should put this in chat. I will do that. So right now we are on the Joy of Vex. Right there. There you go. There it is in chat. And you can take a look at that and kind of follow along. But yeah, so when you're dividing, when you're doing long division, right? And used to, at least now I know math has been changed the way they teach it to kids, at least in the US, and it's kind of crazy. But back in the old days, you'd have, something like 5 and then divided by 2, right? And you would say, how many times does 2 go into 5? Cool. Hey, Toadstorm. Yeah, fit, chramp, xyz dist, prim uv, solve 99% of the day-to-day problems. Yep. You can use pluralize if you're really brave. There you go. Yeah. So, I mean, these functions are all really, really common. Yeah, I didn't want to speak for everybody, but it sounds like, yes, these are things. There's no secret sauce out there in the industry beyond a lot of these functions. So yeah, lots of good stuff to be, these are the building blocks, right, that you have to kind of build your knowledge on top of. So anyways, so if you're saying something like, what's 5 divided by 2, right? They'll say something like 2 remainder 1, right? So that means that you can put 2 into 5 2 times with a remainder of 1. There's 1 left over, right? And so 5 modulo 2 is also equal 1. It's basically just keeping the remainder of that division function, right? And so this is helpful because what that ends up doing then is kind of looping over these values, right? So let's start with something kind of easy like this right here. So I'm going to get rid of all of this stuff here, and we'll set the attribute of p.y equals 2 at ptnum. And then we'll do modulo 5. And I need a semicolon. There we go. So now what we've got going on here is we have this kind of looping, repeating value, right? So it's going to be doing something like this. It's going to go 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 0. So it's going to keep repeating through those. So because what we're doing is we're putting in the point number, right? So that's in this case 0 to 900, and each time it's dividing that by 5 and outputting just whatever the remainder is, right? So in this case, the remainders go 0, 1, 2, 3, 4, 0. So 0.5, right? If you divide 5 by 5, you're not going to have remainders. The remainder is 0. Right? Because it's a 1 and there's no remainder. So any multiple of 5 is going to be 0, and it's just going to keep repeating like that, right? So that is, hopefully you can start to kind of visualize just in and of that one concept right there, how powerful something like modulo can be when you're making code. So hold on, let me just get rid of our spare parameters down here. So we're talking about, in this case, point number, right? That's why this is kind of this repeating, sawtooth kind of pattern looking thing here, this sharp kind of edged thing going on here. But it can also here work on fractional values as well. So instead of doing p.y, let's do something like cd.r. So we'll do the red, the red component of color. And what we'll do here instead is we'll say something like at time, and we'll do modulo 0.7, right? So now what this is going to do is as we go through time, we're going to have this kind of repeating value here, right? And so it might not be super, super obvious here, right? But it's basically ramping up the red value and then back down. So if we go to, it's going to go up to just right up to 0.675, and then it's going to jump back down and then keep coming back up and then keep kind of flipping around like that in that loop, right? And so since it's 0.7, it's a little, it's kind of a strange fraction, right? So you're going to have some, messy remainders and things like that. So it's always not going to go back down to 0 and up to 1 or whatever. But let's just say we did it to, would modulo maybe like 2 work? Yeah, there we go. So that's going to be a little bit cleaner, right? It's going to go up, 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 and then down like that, right? So maybe modulo 1 instead would be better. So it's just going to do it basically like, once a second, basically. Right, so we can see how we can create these looping values. Say something like time gives you a loop as we run through the time on the timeline. It's going to give us a loop there. Something like ptnum, you can loop across the geometry based on its point number, right? So there's a bunch of different ways that you could take these two concepts alone and build a ton of different effects based on that. So, all right, cool. So we're just going to go back to what we've been doing before and start looking at kind of how this maybe works in that length at p function. We're going to go back to that. So let's do that. Let's do float d, and we'll set that equal to the length of at p, just like that. Great. All right, so then we'll take d, and we'll multiply that times equals by a channel. We'll call that scale again, right? So we're kind of back to where we were. And then again, we'll do at p dot y equal to d. So we're setting the y component equal to d, right? All right, cool. And we need to add in this channel. So we're just going to add in a spare parameter right there. And now we're kind of back to right where we were. We have this scale in order to make this kind of smooth, funnely shape here. Okay, so what he's saying here is that, so how can we make this a stepped function instead of a smooth, increasing fractional value? Because like right here, you can see the p dot y is showing that value that we had output, right? And if we sort this, we're going to see that they're going to be going, smoothly up to each of these values, right? So we're starting way down at 0, and it's going 0.1, 1.1, all the way up. What if, and he's saying if you removed after the decimal place, you would get something like this, a bunch of 1s, then 2s, then 3s, right? Because if you took off this end part of the decimal, that's going to actually start to step it, right? But then what if it's a really small value, right? Say ranging from 0.001 to 0.003, right? Well, if you remove the decimal point there, that doesn't give you a stepped value, right? Because it's all 0. So that doesn't really do us anything good. And similarly, he says here, anything that's 1,000 to 4,000, if we tried to take the decimal off, it's not going to make a difference either. So what we need to do is bring these values into a place where cutting off that decimal will actually give us a benefit, right? And so we can actually use a really cool function called trunc in order to cut off those decimals, right? So let's move on to this next function here, and we'll see how this allows us to cut off those decimal values, right? So here we have our scale, right? So we have our scale, and I'm just going to move this down one. And let's add in another float f, which is our factor that we're going to scale it, our values we're going to scale by, right? So let's take that and we'll say float f. This is our factor. I want to say equal to ch factor, like so. And then what we're going to do is we're going to take d and we're going to divide it by f, like this, right? Then we're going to truncate the decimals off of that, right? So we'll say d equals trunc d. Okay, so now we're truncating those decimals off of it. And then finally, we're going to multiply it back by that factor. So we're taking taking our values, right? So let me just finish this off right here. We'll do times equals f, right? Like this. Okay. And I'm going to add this in. And let's just set this factor in here, right? So Durrell is my, it's a very good friend of mine, always making waves out here. He actually was the best man at my wedding, and he is here to, I think, also help Matt just yell from the back and make some comments. So glad to have you here, Nick. Nick is not a Houdini user, but just a friend. So he sometimes will tune into my streams and just enjoy me babbling on, which is what every good friend would do for you, I guess, right? Anyways, okay, so no, Matt, I think everyone's here to heckle. So as long as you all heckle, maybe heckle in a helpful way, then we'll get to a good end result. I think. Yeah, I think Toad is here to heckle you, and then you're here to heckle me, and maybe I'll heckle. Yeah, we'll just be just kind of this round of heckling. It'll be great. So anyways, what we're doing here is we're taking, we're using this factor, right, to scale our value into the range where we can cut off that decimal effectively using that truncate function. And then once we've done that, we're going to scale it back up by that factor as well. So we're scaling down and then scaling up. So this is kind of an interesting way to use this truncate function, right, to be able to actually see, to be able to step, and in this, what this term is quantize our data, right? So you can see here, this is same thing that Matt was playing around with here. And as we adjust these values, right, we're going to get more or less, scale of this original shape. And then as we adjust this factor, that's going to change how much we're quantizing this data, right? How kind of wide these steps are going to be as we're shifting them. And I kind of think there'd be an interesting thing to do here. And I'm just going to kind of go off the script a little bit because I kind of want to show those values real quick. So let's just look at what D looks like here. So let's just add in a couple attributes that we can just visualize real quick. So we'll say at, let's see, this is factor. We'll just say fact D, something like that, equals D at that spot. So that should give us the unfactored like the factored value of D. And then let's do here, we'll say trunc D equals D. So since we're doing these things along the way, this should update it and start to adjust these. Okay, cool. So it is working. Actually, what I'm going to change these around so they'll be next to each other. So we'll say D trunc, and we'll say D fact, like that. Okay, cool. So now what we can see here is these are the two values that we're dealing with, right? So we're taking this, we're using this, I'm just going to kind of separate these apart so we can see what's happening here. So we can just separate them out there. So these are kind of the different steps, and we're just outputting this as like a visualization so we can see the numbers here. So Okay, so we have this D value that's coming in here, right? And once we divide that by F, that's kind of this factored value, right? So as we change this factor right here, you can see how this value is going to be changing quite a bit. So we're scaling it down, right? So you can see how these values are getting kind of closer and closer together in how far the decimal is from each other. So they're getting closer and closer to each other. Then when we truncate it, we're cutting off these decimal places here and just getting this 3.0, right? So as we scroll down here, we can see, okay, this 3 goes to 3 there. So we come down here, 2.3. Okay, that goes to 2. And that truncation of that value then gets multiplied back by this factor here, right? So the truncated value is 2, but as we multiply that by 3.4, that's going to put us to 6.8, right? So we're basically starting with, here we can see what the D original is. We'll do that here as well. So let's do at D orig equals D. So the reason we can do this each step of the way is because we're doing these divided equals truncation of D. So each time we're updating the value of D, so we're writing out these attributes kind of along the way, and that allows us to spit those out. So this is maybe a little bit more in-depth stuff that we wouldn't maybe normally see, but hopefully this is going to give us a little idea of what is happening here. So we're starting with the original values. We're multiplying it by a factor here. Yep. Oh, sorry. No, I didn't need to do that. That wasn't really even the right thing. But anyways, you can see what's happening here and how we're basically truncating these values. So so that's the idea that we've got going on here. I'm not going to entertain that, Toad, but I think that is an interesting observation. This is a family stream, so we're just going to say yes. I'm not sure what's going on with the scaling of D, but it's happening. Anyway, so all that to say, we're quantizing these values here, and we're getting this stepped function because we're taking off that extra fractional bit after the decimal place and just having these round numbers coming out of it, right? So just to kind of clean it back up to where we were originally, we will do this, and there we go. We're kind of right back to where we were without all those extra variables and things like that, right? So hopefully that it clarifies it a little bit and shows kind of what we're doing when we're chopping off those values and why we're multiplying it back up by that same factor, basically. So we're dividing it, truncating it, multiplying it. And that basically brings us back to where we were more or less, but just with this stepped appearance. Great. So the next thing we're going to talk about is actually kind of making a fake truncation, but with a ramp instead. So this is an equally valid way of doing it is by doing a stepped graph, right? And there is actually a neat way of doing that. You'll see that this little GIF here is going to show us. So let's just set up this Vex first, and we'll kind of talk about it as we're looking at everything here, and then we will, so then we'll talk about how to set up these stepped ramps here. So, all right, we'll go back, get rid of this stuff in here because we're going to change this around a little bit. I'm going to get rid of my delete the spare parameters here. So let's do D times equals, and we're going to make a channel. And this is going to be called pre-scale. Alrighty. And then let's do D equals ch ramp. And this is going to be called my underscore stepped ramp, like that. And then we'll do my stepped ramp of D. So we're going to be evaluating this ramp over the variable D. And finally, we'll multiply this D variable by a post scale. So we'll say ch and post underscore scale, like so. And then finally, we'll set the y component of the position equal to the variable D. Great. So let's hit our little add spare or evaluate spare parameters. So we've got our pre and post scales here, and we have a stepped ramp that we're going to work with. And so what we can do here, let's just look at maybe some of these values that Matt's working with here. So yeah, so let's do like a little bit of a scale first, and then we can do a bit more here after the fact. And I have a feeling, nope, okay, there we go. Cool. So we can do our pre-scale here, get something interesting looking like that, and then we can always adjust the post scale here, right? So this is maybe a little bit of a nicer verbiage to think about with this, with the pre-scale and the post scale, because we're scaling, you know, the variable d once we've calculated the length of it from the origin, right? And then we're evaluating the ramp, and then we're scaling after that to set the final height of it. So yeah, so as far as setting the ramp with in order to set it to these stepped kind of values, what we can do is we can actually, we'll take this away and just leave 1 point like that, and we'll set this to constant, and we should be able to now add in more stepped constant values like this, right? And so constant values are really going to work. You know, you can see obviously this is making a stepped value here, right, in this ramp. And what we'll be able to do is now have this evaluated across, you know, across our ramp, right? So we're going to, oh, there you go. Yes, bonus lazy. That's right. So here there is actually a steps. That's right. So if you want to just do it super quick, there it is right there. There's all sorts of different ones in here, right? So we can just go around and click a whole bunch of different random stuff, right? But yeah, sure, there's steps. So bonus lazy from Matt himself. I went the hard way. I always seem to find the more difficult way of getting to a result. So anyways, so yeah, so basically what we're doing here is we're taking this, it's very similar to what we were doing before, but instead of using linear points to be able to look up our attribute or our variable d in this x-axis here across this ramp, we're now using, instead of linear points, we're using constant points and constant interpolation to kind of set the value. You know, after this point, everything's set to 0. After this point, everything is set to, 0.333. Here it's 0.6666, and here it's just 1. And obviously we can evaluate, you can change these however you'd want, and those will follow accordingly. You could add in more steps, you know, here. So maybe we wanted it to be really stepped in there. Maybe we'd move it out like that or something. You can move these around, whatever. So there's obviously a lot you could do here to be able to create a bunch of different looks and feels to how this would evaluate. But more or less what we're doing is doing the same thing we were doing before, however, just using these constant interpolated points to be able to create those steps. So this is basically faking that same thing we did before by just using a ramp. And so just what Matt was saying here, some of the defaults is you set prescale to 0.1, like that. Actually, that's not right. Huh. It's kind of odd. Yeah, that does seem to make sense to me, but for some reason that's not the case, and that's because, oh, maybe the grid is a different scale now. That's probably what it is. Yeah, so it's probably like is it like 0.05 or something probably? Yeah. That's probably what it is. Anyways, so they changed the default size of the grid. Oh, no. I have a uniform scale on here because I was screwing around with it before. That's why. My bad. This is why I should use a clean one every time. My bad. There you go. So it's 0.01 or just 0.1. There we go. Now it's doing what it should be. Anyways, so that's why that scale was looking a little strange, because we were scaling it already. The whole grid was scaled up. Great. So hopefully that is gives you a good understanding of a couple different ways to be able to make like stepped values and stepped, make stepped functions and things like that. You can use, quantizing, or you could use a stepped ramp to be able to create that kind of striated looking geometry or values or whatever you might be trying to do with your functions that you have in your Vex. So that kind of wraps up day 5. Just a couple exercises here that I would suggest you going through and trying out. You could try different interpolation modes on the points of the ramp. You saw some of those just when I was flipping through on these different presets here. Using the interpolation, how can you set a sine wave with as few points as possible, right? What kind of interpolation could create that nice smooth sine wave? And then what other inputs can you use to drive a ramp? Maybe components of position or color or of a normal. Current time, current frame. And those things aren't always going to be in a range of 0 to 1, right? So how do you fit them into the range you need, right? So that's something to think about. And those are things that you're kind of always doing when you're working with Vex is taking values in different ranges, fitting them, having things do what you want to do with them, and then maybe putting them back to that, or many other different things that you might do after the fact. But so yeah, if wow, that was super delayed. I pressed it at the start of the stream and there pops up my message. It's really weird. Anyways, yeah, that is the end of day 5. So we'll be wrapping up the stream shortly. If you guys have any questions or thoughts about what we talked about today, I'd love to hear about them before we sign off for the day. Hopefully our little sidetrack there didn't get you too far off as far as learning these concepts, but I think all of the information there is still obviously super valid. There were just a few things we had to do to tweak how the ramps worked and things like that to get to our final expected output that we would see in these examples here on the site. So, if anybody has any questions, like I said, please drop it in chat. My plan, like I said, was to continue doing these streams hopefully 3 times a week, Monday, Wednesday, Saturday, in order to get through this data or get through these different lessons kind of in a timely manner. And I was kind of excited to do Saturday because I figured some of our... Oh gosh, no problem at all, Matt. Thanks for making the updates live as we were doing it. I'm glad to have you here, and you're always welcome to watch along if you for any other fixes or any other errors on my end. That's always super welcome. So thank you. So hopefully if you're maybe in Europe or whatever, maybe 1 p.m. Eastern time, will be much better for you to be able to kind of watch along live. I want to try to make sure that we're able to get people in all different parts of the world, maybe a chance to watch and join along. So I know obviously Matt's in Australia, and some people are in Europe, and it's hard to get all the time zones working together, but hopefully doing something like that will at least give a chance for some people to be able to join in and be a part of it live. So it's always good to be able to ask questions. And please, if you are watching these and have any questions, you can feel free to put them in the comment section under the video. I've been trying to keep track of all those comments. So if there are questions or anything that you're struggling with, you can always drop questions in there. And HoudiniHangout.com, you can find a Discord invite to my server that I run for this community. You can ask any questions in there, and certainly if you are a yeah, see, there you go. Matt can't make that one because that's too early for him. So that one I'll be on my own. I'll be flying solo. But if you want to get in touch with Matt nice and easily, I believe if you go down here at the bottom of his page, you can click on the PayPal or Patreon links. And if you become a Patreon of his, I believe you get access to his Discord server as well. So you could drop some questions into his community as well and ask those folks there. They're really helpful and super kind as well. So yeah, so hopefully if you guys run into any issues or anything like that, just from some of our little kind of on the fly corrections, I'd be happy to answer them in the chat. So feel free, or in the comments. So feel free to drop them in there. But yeah, so it doesn't look like we're getting any questions here. So I'm just going to start wrapping things up. So thank you all so much for watching. Hopefully 3 lessons in a day isn't too bad, but hey, if you need to, just stop the video and come back later. I'm going to be putting, there should hopefully be chapter markers in here within, as soon as I can get in and edit it and make some trims and things like that. So I'll be putting chapter markers in so you can follow along and things like that. So yeah, well, thank you again, everybody, for joining. Thanks, Matt, for making some changes on the fly. Super appreciated. And again, Wednesday and Saturday we'll be doing streams on those days as well, as long as nothing goes wrong in my personal life or whatever. But that's the plan as of right now. So unless some major catastrophe happens, which I will be sure to update if any changes happen on social channels and on the Discord server. So another good reason to join there, so you know if something changed last minute or whatever. So anyways, thank you guys again so much for watching. I really appreciate it. It's super fun to get to chat with all you guys about all these different questions and comments and things that we're all kind of working through. So yeah, thank you for being here, and I will see you guys next time. See ya.